diagnostics in application, diagnostic plots, residuals, all the types and flavors. It's the bread and butter, baby. What's your jam?
Howdy do, Bio 6611. Welcome to this week's set of lectures, which was going to start with residuals. Before we dive into that, though, we're going to revisit some of those assumptions for linear regression and then define the various types of residuals we may be leveraging or encountering this semester. We'll end with a brief teaser of how we can also leverage our residuals to actually evaluate our model assumptions before digging a little more into that in a subsequent lecture. So let's start with revisiting those linear regression assumptions. Recall previously we discussed them as existence, independence, linearity, homoscedasticity, and normality. Very briefly, existence was that idea that for any value of x, y will be a random variable that has a finite mean and a variance in a given probability distribution, in our case, normality. Independence is going to be that the y values are statistically independent of one another. Linearity is that for any value of y given x, we can approximate that relationship with a straight line function. Homoscedasticity was the idea that the variance of y will be the same for any given value of x, or in other words, sigma squared for y given x is equal for x equals 1 up to x equals little x. And finally, normality. For any fixed value of x, y will have a normal distribution. Now we should note this doesn't assume that y itself is normally distributed, just that y given a predictor x will be normally distributed. And a few other useful things to highlight about that normality assumption. It's actually not required to obtain those estimates of the regression coefficients we previously derived with the ordinary least squares approach, those betas. However, if we want to perform a statistical test or obtain confidence intervals, we do need to rely on that assumption of normality in order to have accurate conclusions. However, if we happen to have a large enough sample size, then the estimates could be considered asymptotically normal. So then even if something does not appear normal with, let's say, y given x, if the sample size is large enough, we may be able to leverage that idea of the central limit theorem in some asymptotic normality. So with those assumptions, how can we actually evaluate if we've met them? And in some cases it will be context specific, but in many ways we can use regression diagnostics. And there's really two types of ways we'll use them in this semester, one more frequently and one less often, also kind of corresponding to practice. More often we'll use regression diagnostics as a tool to assess the linearity, homoscedasticity, and normality assumptions of the linear regression model. Many times things like existence or independence will be evaluated based on our context. Another place, though, that we can use regression diagnostics that we'll touch on more deeply later in the semester is how we can identify outliers and potentially influential points in our data set that may be affecting the results of our regression model. One of the other things to note is that with linear models, frequently the assumptions of linearity, homoscedasticity, and normality are extremely interrelated. And so many times if one is violated, it's likely the other ones may be violated as well. However, on the flip side, actions taken to maybe correct one violation, if they're not all violated or one appears to be more violated, could result in a kind of domino effect to a violation in another assumption. For example, a transformation to stabilize the variance could potentially lead to nonlinearity, giving a trade-off of these different assumptions we're trying to meet. Before we fit any regression model, it can be a good idea to look at simple descriptive statistics for potential data errors, extreme outliers, or any other potential violations of our assumptions. And these could be univariate statistics, such as the mean, standard deviation, the range, histograms, or bivariate descriptive statistics, correlations or scatter plots. And these are the ones that we'll focus a bit more on later when diagnosing our residuals. So with that, let's move on to actually introduce the families of residuals that we may encounter and what their definitions are and some of their properties. But first, let's remind ourselves why we're even interested in calculating the residuals. And it gets back to that idea of the error term in our true linear regression model. In our regression analysis, we are assuming that the unobserved error terms, epsilon sub I, have those assumptions we've made before, that they're independent or uncorrelated with one another. They have a mean of 0, a common equal variance, sigma squared y given x, and they follow a normal distribution, which is again required for performing those parametric tests of significance or calculating different types of confidence intervals. However, it's important to note that this is unobserved. We actually don't know what the errors are. Because of this, what we do observe are residuals, or what we call residuals. That's saying whatever our actual observed value for yi is, we'll take that difference from the predicted value from our regression equation and use that to try to estimate our unobserved error term. One of the catches to make, though, is that the residuals are not independent random variables, since we force them to sum to 0 by the way we derive our best fit linear equation. However, in most cases, if the number of residuals is larger relative to the number of the independent variables in our model p, which in our case for simple linear regression is just 1, the dependency effect here can, for most purposes, be ignored in our analysis of the residuals. One thing to note here is that when we look at examining our observed residuals or potential functions of observed residuals, we can use those to see if we violated any of our ordinary least square linear regression model assumptions. And so we're going to walk through in the next few slides 5 different types, starting with our observed and then introducing different flavors and twists on them. So let's start with that observed residual. It's by far the most straightforward one because we've already defined it a few times, and it's something we just get directly out of our model by again taking the difference of the actual observed outcome we have and the predicted value for the outcome for a given individual. As we stated based on our assumptions, the observed residuals have a mean of 0. They also have this variance term we could calculate if we needed to or were interested in, which also corresponds to the residual mean square error, or MSE. And we can note that this then, of course, is that assumed normality distribution of our residuals, or the underlying error. One of the limitations, though, to using observed residuals only is that the magnitude of them will depend on the scaling of y. If we have one problem where y varies from 0 to 1,000 and another where it varies from 3 to 4, we're going to have a very different range of what those residuals may be. And this can make defining general rules for evaluating them and their properties challenging. So we have some different methods for standardizing the residuals that have been developed. That leads us to our first twist on the observed residual, which we call the standardized residual. Or in some cases or sources, it's known as the semi-studentized residual. And it's simply the observed residual divided by the square root of the mean square error. And so we see here this nice little equation on our screen. Z sub I, our standardized residual, is literally just equal to that observed residual E hat sub I divided by sigma hat y given x, or the square root of our mean square error. Because of this, we have a mean of 0 and a variance of 1, because what we've essentially done is that idea where we have, let's say, a normal distribution with some mean mu and some variance sigma squared. When we transform that to a standard normal distribution, it now has mean 0 and variance 1, which is essentially what we've done here. And that's nice because we can think of it now, if we just sketch a little normal distribution out here, if things are perfectly centered and we have no violation of our assumption, we should have something that looks very close to a standard normal distribution, where we even know, for example, that between about -2 to +2, we should have approximately 95% of our data falling within that range. And so it can give us a good gut check of how appropriate that assumption may be. However, there are other twists to make on these assumptions, and part of this comes down to some other nifty properties. For example, we also have what we call the studentized residual. And this is the observed residual divided by the standard deviation of the ith residual. And so in other words, for each residual itself, we can calculate the variance of that given quantity, which we have here as the MSE times this quantity 1 minus h sub I, which we'll define here in a second. But before we do that, we can note that we have our equation here written in a few different ways, but we can see there's this direct connection from the standardized residual we just discussed and this h sub I term, which is the leverage. This can be thought of as a measure of the importance of that ith observation in determining model fit, and is also an element of the hat matrix, which we'll discuss both of these in greater depth later in the semester. Studentized residuals have a mean near zero, but not exactly zero, and also have this variance formula here, which will be slightly larger than 1. So we're not quite fitting, again, that standard normal distribution anymore, nor is it exactly following a t-distribution, but it does approximately follow that t-distribution with n minus p minus 1 degrees of freedom. This brings us to the deleted residual, which is also in some cases known as a press residual. It represents the standardized residual, but with the current observation deleted in the estimation of the betas, and therefore it's not taken into account in the calculation of the MSE. Specifically, we have a simple looking equation here where d sub I, the deleted residual, is equal to our observed outcome y sub I minus that predicted value for that observation that's being predicted from the model where the beta coefficients were estimated without it, where it was deleted from the data set. The challenge with this approach, though, is that we would have to fit n different regression models. We'd have to go through and remove each person once, fit the data with everyone remaining, predict their value, and do that over and over again. Fortunately, we have this slightly simpler representation with d sub I equal to e hat sub I divided by 1 minus h sub I, or our leverage. Now, the catch here is that this statistic itself is not the most useful calculation for all of our residuals in our context, but it is worth noting that it's used often in predictive modeling to calculate what we call the press statistic. And that's the sum of the square of our deleted residuals for predictive modeling purposes. However, in our case, it's most useful in its calculation and how it leads to jackknife residuals. And this leads us to the jackknife residual, which may be the crowning champion for the most names for a term that we have this semester. They're also known by studentized deleted residual, R-student residual, studentized press residual, externally studentized residual, and probably some more names as well that we don't have on the slide. What it does represent, though, is that studentized residual with the current observation deleted in the calculation of the ith jackknife residual. So specifically, we say for that ith person or observation in our data set where I ranges from 1 up to n observations, we would remove them from the data set to do this calculation for things like the MSE with the ith person removed. Obviously, this would be a challenging one to estimate as well if we had to fit n different models over and over again just to get this calculation. So fortunately, we've been able to show that it can be represented instead as that studentized residuals as a relationship with the sample size and the number of predictors. One of the nice things about jackknife residuals is that it has a mean near zero, and this variance, as we've defined here, that is also slightly greater than 1, but rather than approximately following a t-distribution, it will exactly follow that t-distribution with n minus p minus 1 degrees of freedom, or n minus p minus 2, if we want to simplify that a little bit. And so how are these actually useful and leveraged in practice? How can we examine the residuals? We can first note that if our standard regression assumptions are satisfied, and approximately the same number of observations are made at all predictor values, then the patterns in each of our types of residuals will look pretty similar. The reason we like things like studentized and jackknife residuals, though, is that they help to make suspicious values look more obvious relative to these other residuals. And in fact, jackknife residuals are even more sensitive and tend to be the most preferred for this reason when using residuals for regression diagnostics. And we'll see this play out in the actual application of evaluating our assumptions in some examples. The standard normal distribution can still be useful if we happen to have the degrees of freedom, n minus p minus 1 for the studentized or n minus p minus 2 for the jackknife, at a fairly large size, usually something much above 30. The reason this is nice is that in those cases our t distribution can be increasingly approximated by a standard normal distribution. This is useful for evaluating the size of observed residuals and for identifying outliers because we can appeal to the properties of a standard normal distribution, where again we might expect that no more than 5% of the residuals would exceed 1.96 in absolute value. Again, thinking just about that standard normal sort of distribution where if we have negative 1.96 and positive 1.96, we expect about 95% of our sample to fall within those two values. Therefore, if we did see a larger percentage of observations in either one of these tails, we may be suspect that our assumptions have been met. Since calculating these values by hand could be tedious, we'll instead introduce some ways we can do this in R. For example, we can generate some data to fit a linear regression model to, setting our seed for reproducibility. We'll simulate some predictor independent variable x, and then we'll calculate a outcome dependent variable y based on a regression equation where we have an intercept of 3 and a slope of 2. With this simulated data set then we can fit our linear regression model with the GLM function, and we see that in fact based on our simulated data set of 100 observations we have an intercept near 3 and a slope near 2 as we defined. Now, the nice thing about GLM is that the observed residuals can be extracted as an object from our output or that function there, just using GLM1, our restored result of that linear regression, $residuals. Now again, because those depend on the scale of our outcome each time, we may be more interested in pulling something out like the Jackknife residuals. And here in R we have it termed that RStudent residual, but we can literally put in the function RStudent, the object that we've stored our linear regression results in, GLM1, and we can see then the observations here, how they correspond between the two for that transformation from the observed scale over to that exact t distribution for the jackknife. Visually, we can see what it looks like here on just two different plots, where again we can note that the observed residuals have quite the range from about, I'd say, negative 15 up to a little higher than 15, whereas the jackknife residuals, because of that standardization and that process of deletion, follow that exact t distribution and range in that window of about negative maybe 2.5 up to about 3. What we'll see in some examples in other lectures this week and later on is a quantitative examination of the residuals. They can be used graphically or formally in tests to evaluate potentially the skewness, kurtosis, normality, homoscedasticity, and independence assumptions or distributions that we're looking at. And so with that, we'll pause here and then get ready to look at some ways we can look at them graphically through diagnostic plots.